When astronauts stand on the surface of the moon, they will be part of what President Kennedy called the most hazardous and dangerous and greatest adventure on which man has ever embarked. But man hasn't arrived there yet. There is still a lot to be learned about this strange, hostile world. As far back as 1959, plans were being made for exploring the surface of the moon with unmanned spacecraft capable of photographing it, analyzing it, and measuring it. In July 1964, Ranger 7 crashed into a remote corner of Mare Nubium, taking over 4,000 pictures of the lunar surface on its way. It took the first close-ups of the moon, and in recognition of this achievement, the area was named Mare Cognitum, sea that has become known. The success of Surveyor 1 is almost legendary. It soft-landed on the moon in the ocean of storms on the 2nd of June, 1966, and returned over 11,000 photographs of soil, rocks, and topography. It showed the color of the moon's surface and recorded the changing temperatures for more than 3 lunar days and nights. Ranger and Surveyor are part of a carefully planned series of missions designed to photograph and explore the moon's surface and to find the best landing sites for Project Apollo, the manned lunar mission. The third of these unmanned missions is Lunar Orbiter, in which an orbiting satellite takes pictures of the moon and transmits them back to Earth. Over 50,000 square miles of the visible moon's surface have been photographed with 100 times better resolution than has been possible with Earth-based telescopes. 6,000 square miles of it nearly 1,000 times better. Lunar Orbiter is best described as an orbiting photographic laboratory. Unlike earlier photo missions which used a television type of camera, Orbiter takes its pictures on 70mm film. It develops the pictures and stores them until it is time to send them back to Earth. The whole craft is similar to a 4-leaf clover with a thick stem. The leaves contain the solar cells that provide power for the various systems on board. And the stem contains the 2 lenses, the film processing unit, the picture transmission equipment, and the various scientific instruments, such as micrometeorite detectors and radiation counters. At the heart of Lunar Orbiter is the photo system. Pictures are taken simultaneously with the 2 lenses, one close-up and one wide angle. A device called a velocity height sensor determines the speed of the spacecraft relative to the moon's surface, normally over 4,000 miles an hour. As an exposure is being made, it moves the film proportionately to avoid blurring the image. The film then moves into the processor, where it is rolled into contact with a bimat web, a material that has been soaked in a solution that develops and fixes the image. It is then separated from the web and dried. The method of getting the picture from the moon to Earth is one of its most exacting tasks. The film is scanned by a light beam 1/20th as thick as a human hair. As the beam passes through the film, its intensity varies as the density of the image varies, and this variation is detected by a photoelectric cell. This converts the light into electronic signals which are transmitted to Earth. They are then converted back to light, and the picture is reconstructed. Each frame, consisting of 1 close-up and 1 wide-angle photo, requires 45 minutes of transmission. A typical Lunar Orbiter mission begins, after all of the checkout procedures have been completed, with the orbiter perched atop an Atlas Agena launch vehicle at Cape Kennedy, protected by a magnesium shroud.
3, 2, 1, 0.
The Atlas ignites, pushing the spacecraft through the thicker atmosphere. After a little more than 5 minutes, the Atlas engines shut down and the stage separates and falls away, followed in a few seconds by the shroud. The Agena second stage engine ignites long enough to place the combination into a parking orbit, a temporary one about 100 miles high, where the attached vehicles coast. When they arrive at an acceptable position from which to head for the moon, the Agena's engines ignite for the second time, boosting the spacecraft out of its parking orbit. The Agena then separates, sending the spacecraft on its way to the moon. Then, on command from Earth, the lunar orbiter begins to assume its familiar shape. The solar panels fold out to pick up the sunlight, and the radio antennas are extended for communications with Earth. A sensor locks onto the sun, aiming the panels so they can begin transforming the sun's energy into needed electricity. Several hours later, another sensor, designed to respond to Canopus, the brightest star in the southern sky, picks it out and locks on it. These two lock-ons are necessary so that ground controllers know the position of the spacecraft for future maneuvers. For the next several hours, the course of the spacecraft is carefully plotted against the known path of the moon. A decision can be made that a mid-course correction is required for perfect aiming. This is accomplished by rolling and pitching the spacecraft to the desired attitude and firing the velocity control engine a given period of time, either to speed it up or slow it down relative to the speed and direction of the moon itself. Orbiter 3, for example, was so accurately started on its way that it needed only a 500-mile adjustment in its initial aiming point. The orbiter arrives at the moon at a speed of about 4,500 miles per hour. If this speed is maintained, it will pass the moon and go on into an orbit of the sun. Once again, at the appropriate time, the spacecraft's attitude is adjusted and the engine is fired to slow it down to 2,200 miles per hour. It is attracted by the moon's gravity and swings into lunar orbit. For several days, the controllers study its orbit to determine precisely where it is. Then, for the third time, it is properly oriented and its velocity lowered to drop it down into its picture-taking orbit, ranging from 1,150 miles to about 28 miles. It is ready to start its photographic mission. The first three orbiters have succeeded in pinpointing the potential landing areas of Apollo, the manned lunar mission. They have returned excellent photographs of the far side of the moon, 10 times better than Earth-based views of the front side. They have surveyed vast areas of the moon with an accuracy never before attainable. They have shown us the ruggedness and the smoothness and some of the complexities of existence in an airless void. They have shown us the Earth as it appears from the moon and opened our eyes to the possibilities of planets like Venus being capable of supporting life. They have shown us our Surveyor spacecraft on the surface and Ranger in it. They have given scientists a wealth of material that will take years to interpret properly. They have assured us that micrometeorites in the vicinity of the moon are hardly more hazardous than near Earth. They have determined the exact size and shape of the moon and accurately defined its gravitational field and its mass. Because results of the basic mission have been achieved, other accomplishments have been made possible. The first lunar orbiters, for instance, surveyed 0.5% of the moon's face. Orbiter 4, in a polar orbit at a higher altitude, photographed 99% of the near lunar surface at a resolution 10 times better than that available before. A team of scientists has outlined over 400 sites they feel are of great scientific interest, many requiring oblique photos, like the startling Copernicus pictures, giving us a different perspective on the lunar surface. Lunar Orbiter, along with Ranger and Surveyor, have added significantly to our knowledge of the moon and its origins. And what is more important, they have provided a solid foundation upon which to base the important decisions that will give our total lunar exploration program meaning and direction in the future.